Alright, so let's recall that in the previous video we saw those two corollaries, and today we are going to apply them to solve some geometric problems, concrete geometric problems regarding constructibility. But before we do that though, we need something else also, and that's why I have created this special exercise. So this exercise is about constructibility of an angle and constructibility of the cosine of that angle. You remember that by definition an angle is said to be constructible if it is an angle between two constructible lines. That's how we define constructibility of angles. So this exercise claims that that is the case if and only if the cosine of the angle is also a constructible real number. So let us first establish this fact and then we will see what comes next. How using this and those corollaries we will answer some geometric things. Okay, now in the beginning itself we can dispose of one case, namely when theta is 0. You remember that in any of our construction we start with those 2 points which are given in the beginning itself, and we have called them P and Q, capital P and capital Q, and the distance between them, they are constructible by definition, and the distance between them is 1, and the line that passes through them is also by definition constructible, and the angle between this constructible line and itself is 0 degree, of course. So again, by definition of constructibility of angles, 0 degree is a constructible angle because of this. On the other hand, what is cos 0 degree? It is 1, and 1 is a constructible number. It belongs to the field of constructible numbers W. Why? That's because W is a subfield of R, the field of real numbers, and hence it must contain every rational number, and as such it also contains 1. We know that any subfield of R contains all the rational numbers. In that sense, the rational numbers form the smallest subfield of R. So that means 0 degree is a constructible angle and the cosine of 0 degree is a constructible real numbers. So that means in this case our claim is true. So we can now assume, I'm not going to write things formally in this solution. Instead, let's just see what this thing is all about. How one can write the solution. Let's just see that. So our assumption now is that theta strictly lies between 0 and 180. And in this part, we start by assuming that theta degree is constructible. Let this be constructible. That means what? It means that theta degree is an angle. I am saying an angle and not the angle because between two lines there are two kinds of angles, right? It is an angle between two constructible lines. So that means now we will have two constructible lines, so that one of those two angles, actually there are 4 angles, but they are, two of them are equal and the other 2 are also equal. So we now have some constructible lines. Let's call them L1 and L2, so that this angle between them is theta degree. Keep in mind that this can be obtuse also. That depends on what theta is. So this L2 may be like this. Okay, but this is just one of the 2 cases. Alright, so now what happens? We also know that when two constructible lines intersect, then their point of intersection is also by definition constructible. So this S is constructible. Let's call this point S. Alright. So S is a constructible point. Now let us draw I don't know if I will be able to do it properly, but you get the idea. Let me just draw a circle whose center is S and whose radius is 1, say. Then this circle is constructible. Why? A circle by definition is constructible if its center is constructible and its radius is a constructible real number. And that is the case here. S is constructible, we have already seen, and the radius is 1, which is a constructible number. Okay, being a rational number, it's constructible. So this is also constructible. The lines are constructible. S is constructible. And now look at this. These constructible lines are intersecting with this constructible circle at these 2 points. Say, let's call this T and this point U. So T and U also by definition are constructible because they are points of intersection of constructible objects. Now if we join T and U by this line segment, then the length UT, that positive real number, that will be the length of UT, that will be constructible. But why? Why is UT constructible? Keep in mind, UT is a real number. It's in fact a positive real number, and we are saying that this real number is constructible. Go back to the definition of constructible real numbers. When do we say that a real number is constructible? Namely, when we find two constructible points in the plane such that the distance between those 2 points equals the absolute value of the real number. In this case, we do not have to bother about absolute value because it's positive. So the absolute value will be the number itself. But this, of course, is the distance between two constructible points, and they are U and T. So that is why UT is constructible. Okay? Right. Now, from triangle SUT, we have, if in this triangle you think of the law of cosines, which is a result that you should be familiar from your trigonometry. By that law of cosine, it started raining. Anyway, cos theta degree is going to be what? SU square plus ST square minus UT square divided by 2 times SU times ST. Okay, so we will get this from the law of cosines applied to this triangle. But now we know some of the values here. Do not forget that our circle has radius 1. So that means SU and ST are both 1. So this thing becomes what? 1 square plus 1 square is 2 minus UT square divided by 2. Now 2 is a constructible number and so is UT. and the constructible numbers form a field. So that's why this quantity is again in that field, and that's how cos theta degree is constructible. Okay. So that means we have proved one half of our claim. Conversely, let cos theta degree be constructible. Now we have to prove that theta degree is constructible, and for this one the arguments go like this. So now we are going to go back to those points P and Q that are initially given to us. Say we have P and Q and we draw x and y axis in such a way that this is P, so that P becomes the origin and Q lies on the positive x-axis. If we specify this, then that means we have specified precisely how we are drawing the axis, right? Well, you can of course ask which direction is the positive direction of y-axis, but actually that does not matter. What we are concerned about here is that Q lies on the positive side of the x-axis, but this is just the positive direction of the y-axis. Okay. Now we do know what theta is, so let's draw the angle theta in its standard position. We already know what that means. It means that the initial ray of that angle coincides with the positive x-axis. So this is the initial ray, and the terminal ray will lie somewhere. Say this is the terminal ray, and then this is our angle theta. But again, let me remind you that this can be like this. It may be a right angle, who knows, or it can be like this also. That does not matter. This is one of the cases. If you draw the other case, there also a similar argument will work. In this case also, it will be the same. You see, if our angle theta is obtuse in this part of the solution, then that triangle SUT will be like this, an obtuse angle triangle. That does not matter because the law of cosine is applicable to any triangle. Like that, here we have this case, say. Okay. Now what we do, here also, just like that one, we draw a circle centered at P and having radius 1. Now P by definition is constructible and the radius is 1, so this circle is constructible. And of course, because the radius is 1 and the distance between P and Q is 1, so this circle is going to pass through Q. Alright. Now, let the point where the terminal ray intersects the circle be, let's just give it a name, U. Okay. And we are also going to draw a line through U perpendicular to the x-axis, and let this line intersect the x-axis at T. You keep in mind that our aim here is to show that this angle is constructible. That means, since this is an angle between this line and this line, now our aim is to show that these two lines are constructible. One of these two lines is already constructible, namely this line. Why? Because it passes through those two points P and Q, so by definition it is constructible because P and Q are constructible. But we still don't know anything about this terminal ray line. Okay, so let's see how the argument goes. So according to this part of the argument, what we first observe is this. Okay. Now the first thing you look at is this triangle PUT. It's a right angle triangle. This time it's a right angle triangle and this is the right angle. So from triangle PUT, what is cos theta? Cos theta degree is base divided by hypotenuse. In this case, the base is PT divided by hypotenuse is PU. But PU is 1 because the radius of this circle is 1. It's a unit circle. So that means this is equal to PT. But our hypothesis is that cos theta degree is constructible, so that means PT is constructible. Okay. So the length PT is constructible. All right. This implies T is constructible. The point T is constructible. But how? And why is T constructible? Okay, now look here carefully. We already know that P is constructible, and now we know that this length PT is a constructible real number. Now if you draw a circle with center at P and radius equal to PT, this dotted circle, then that circle will be constructible. Why? Because the center of the circle is P, that's a constructible point, and the radius of the circle PT is a constructible real number. So by definition this circle is constructible. But now note that T is a point of intersection of this new constructible circle and the constructible line passing through P and Q. So by definition T is also constructible point. This other point on this side is also constructible, but we don't need that. So that's how we are getting that T is constructible. All right. So the line through T and U is constructible. How? By what result? Now this is a result that is already available in the literature. I have just mentioned it, but we have not proved it. Namely, that if we are given a constructible line and a constructible point, then the line that passes through that point and perpendicular to this line is a constructible line. That means you can draw it using compass and straightedge construction. There is another similar result which however we have used in one of the things before, namely that if such a point, constructible point is given and a line is given which is also constructible, then the line passing through that point and parallel to this line is constructible. Okay, so these are things that we are assuming that we already know, and in fact we know them from our elementary geometry classes, those part where we learned construction. So by that result, this line passing through T and perpendicular to this x-axis, which now is a constructible line, is itself constructible. Okay. So that will allow us to next conclude that U is constructible. I think that's the case. Yes. And constructibility of U next comes from this like this. Since U is a point of intersection. This part I am writing because here the steps are somewhat confusing. Confusing means we don't readily see how the steps are coming, so that's why I am writing. Since U is a point of intersection of this line means that like this line, and the unit circle U is constructible. Why? Because we already know that this line is constructible and the circle is constructible, we have already seen. So this point of intersection is a constructible point. So now note that U has been proved to be a constructible point, and we already knew in the beginning itself we had that P is constructible. So the line passing through P and U is also constructible, and that is our terminal line. Combine this fact with the fact that the initial ray of the angle is already constructible, you have now ended up proving that the angle is constructible. So that means we have solved our exercise. Okay, now let's go to the text. Yeah, I think it's quite easy actually if you once more go through the steps, and then you will see that it's nothing very complicated at all. Just we have to see the steps in their logical sequence, and that's just it. So let me just once more go through it myself. P and Q are already given to us, so that's why they are constructible. And we have drawn two axes such that PQ lies along the x-axis and Q lies on the positive side. But why did I take Q on the positive side? Oh, so that I have this length PT positive. Anyway, it does not matter actually. But anyway, we can do this, so we have done it. Next, what we did, we put the angle in its standard form such that this is the, of course, the initial ray, and this is the terminal ray, which can be like this also. Again, let's just see that case. It can be like this. In that case, U will lie on this side and this perpendicular line will be like this. That does not matter, because in that case, this PUT triangle will be on this side. Alright. Let U be the point of intersection of this unit circle and the terminal ray. And by the way, we have drawn the unit circle also. Okay. Now, and then one more thing is that we drew this line perpendicular to the x-axis and passing through U. And that line intersected the x-axis at the point T. Alright. And then from the right angle triangle PT, the first thing we obtained is that PT is constructible. So that's why T is constructible, because of this dotted circle being constructible and T being an intersection point of this constructible circle, the inner one, and the x-axis, which is also constructible. So T is constructible, and hence the line perpendicular to this constructible x-axis and the constructible point T passing through T is also constructible by a result that we should know. Alright. And the point of intersection of this line, I mean the one which lies above, not this one, and the constructible circle is constructible. So that's how we are getting that U is constructible. So P and U are both constructible, so the terminal ray is constructible. The initial ray is already constructible, it always was. So that's why theta is constructible. That's it. That means constructibility of an angle, a geometric angle, is equivalent to constructibility of the number which is the cosine of that angle. Now here we have our first theorem. First theorem means first application. It is impossible by straightedge and compass alone to trisect 60 degree. Okay, so that means you cannot trisect 60 degree. So by this result, we have to show that 20 degree, the angle 20 degree is not constructible, or the same thing, and that's where we are using this result, that cosine of 20 degree is not constructible. So the proof goes like this. The proof will have gaps that will be filled in the exercises. Let alpha be equal to cosine 20 degree. Then cosines are okay, let me just come from that other side. 4 alpha cube minus 3 alpha is 4 cos cube 20 degree minus 3 cos 20 degree. Now you must be familiar with this identity from elementary trigonometry, that 4 cos cube theta minus 3 cos theta is cosine of 3 theta. 3 times 20 degree, that is cosine of 60 degree, which we know is 1/2. So 4 alpha cube minus 3 alpha is 1/2. That means if we manipulate this a little bit, we get 8 alpha cube minus 6 alpha minus 1 is equal to 0, which means what? That alpha is a root of this polynomial. x cube minus 6x minus 1, which of course is a polynomial over the field of rational numbers. So it's coming from this polynomial ring. Alright. Now the thing here is that this polynomial actually is an irreducible polynomial, which we will prove in exercise 7a. This polynomial is irreducible over Q. And that is exercise 7a. We are yet to see the exercises now. So when we will solve these exercises, then the gap will be filled in. So what is it that now we have? The real number alpha satisfies an irreducible polynomial over the field of rational numbers. Since the degree of this polynomial is 3, which is not a power of 2. Obviously, because 3 is not a power of 2, corollary 2 to our main theorem, which will be what? 541, implies that alpha is not constructible. The ancient people must have struggled with these things, but then Gauss came along, Carl Friedrich Gauss, and he developed this theory, and this has this nice application which ultimately settled that this question. There are others also. We will now see that some constructions are impossible by straightedge and compass, of course. Not constructible. And that means theta is also not constructible, which is 20 degree, and that's why you cannot create an angle 20 degree using straightedge and compass alone from an angle 60 degree. So that's essentially the proof. So the gap here is this, which we will see how this is irreducible. The next application is this next theorem. This is 5, no? I brought 4. 5, 4, 3 by straightedge and compass alone. It is impossible to duplicate the cube. Duplicating the cube means if you are given a cube of some side length, cube means that 3D figure, then using only straightedge and compass, you cannot create another cube whose volume is precisely twice of the volume of the original cube. Now, if your original cube has side length x, say, well, in this case, the author has considered side length 1, it's equivalent, you will see why. Then, constructibility of that cube, whose volume is twice the volume of the previous cube, means constructing a cube of side length x such that x cube, that will be the volume of the new cube, will be 2 times the volume of the previous cube, which is 1 cube. But then that x, that side length of the new cube, satisfies this cubic polynomial x cube minus 2 over the field of rational numbers, and this polynomial is also irreducible, and just like there, this one is also going to be handled in one of the exercises. This is exercise 7b. So we will see there itself how this is irreducible. But then again, by corollary to this theorem, since the degree is 3, which is not a power of 2, so x is not constructible. So that side length cannot be constructed using only straightedge and compass. So that is essentially the idea of the proof. And there is one more. It's about a regular polygon. Impossibility of constructing a regular polygon having 7 sides, a septagon. That is the last theorem of this section, and the statement is just that it's impossible to construct a regular septagon by straightedge and compass. That construction, had it been possible, requires us to show that this number 2 times cos 2 pi over 7 radian, of course, is constructible, but this number is not constructible. This is something that is related. You must be able to understand that the cosine here is coming because of our special exercise. Actually, it's all about this angle 2 pi over 7. I mean, if you think about it, the full angle is 2 pi, right? And if you have 7 sides and from the vertices you draw internal lines, they will all meet at the central point. So those central angles, each one of them will be 2 pi over 7. If you are able to construct any of those angles, then automatically you will be able to construct the entire thing, but that is not possible. So that means impossibility of constructing that angle is equivalent to impossibility of constructibility of cosine of that angle. So 2 times cosine of that angle, and this is impossible because there is a polynomial, and that polynomial is this x cube plus x square minus 2x minus 1 over the field of rational numbers that this alpha satisfies, and that fact that it satisfies this polynomial is itself an exercise. So we will see that there, and of course additionally this is irreducible over Q, of course, and that one is exercise 7C. Again, because of its irreducibility and because of alpha being a root of this, and because the degree is 3, which is not a power of 2, the second corollary to theorem 541 implies that alpha is not constructible, and as a result a regular 7-sided polygon cannot be constructed using only straightedge and compass. And this concludes the current section. In the next field theory video we will start solving the exercises, and that's just it for tonight. Tomorrow we have again our usual upload, and tomorrow let's solve ring exercises from Gallian. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.